In this video, we're going to start talking about the first big application of limits in our semester. We really have two main applications of limits that we're going to be using for the rest of the semester. One is going to be continuity, and the other is going to be the derivative. We'll work towards that later, but for now, let's start thinking about continuity. This is one of my absolute favorite topics to talk about because of this first point. The first thing that we're going to do is run into our previous conceptions about continuity and mostly our previous misconceptions about continuity. From there, we'll build up the idea of continuity at a point, one-sided continuity, and continuity on intervals. But first, let's get into our misconceptions. This is always a fun thing to just run into. I want to preface this by saying misconceptions are useful. It is okay to have misconceptions about things because, first off, they're likely not our fault. It's not because we don't understand things that well. It's because of the way that we teach continuity. When we teach continuity, we actually teach the wrong version of it first, which sounds a little strange until we start thinking about other concepts where we learn an incorrect model of something and then we update our knowledge as we go. The one that jumps out to me is this picture here. You could probably all figure out what I'm drawing in a second. I'm going to preface this by saying I am not a scientist, so you might have more of an idea of what I'm drawing than I do. All right, take a second. What is this crappy picture? You don't have to be specific. We can see that this is some sort of atomic model, right? Probably we have an idea of like some sort of a nucleus with electrons orbiting around this. And if you've taken some chemistry or physics or whatever science classes, you probably know that this isn't actually how things work. This is not an actual working model of real behavior at an atomic level. You might know that there's some like quantum mechanics stuff. We have all these electron clouds, these orbitals that are really like probability clouds where we're likely to find electrons. They don't just orbit nicely in these circular movements like planets do. Sometimes people will call this a planetary model of an atom because of it. But that's fine because in a high school science class or a middle school science class, this model is still useful to get some properties, some basic ideas of how things work at an atomic level. We don't need to know every single bit of detail here. So when we think about continuity, we're going to have the same idea happening. We probably have some ideas about what it means to think about continuity of a function. Okay? Those ideas are likely not correct, but they're not correct in the same version that this model of an atom isn't correct. Of course, this is not the way that things work, but this is here to help provide us some intuition and insight without needing to study this big, huge topic of quantum mechanics. So before calculus, we can still talk about continuity at a low level. All right, so think about what your previous conceptions of continuity are. If you want, pause this video, see if you can give yourself some definitions of what it means for something to be continuous. And specifically, we're talking about functions, graphs of things, things like that. So think about what continuity really means in this context. Pause the video. If you want, write some of these down because I think you might be interested to see what my list is going to look like. If you haven't paused the video yet to actually think about continuity, do it. I'm not going to keep going until you pause. Please pause the video. All right, fine, I'll move on. Okay, so our previous concepts, our conceptions about continuity, here's probably what they look like. These are the three things that I hear in my face-to-face classes over and over again from students. A function is continuous if it goes on forever in both directions. All right, here's the next one. A function is continuous if there are no holes, jumps, or breaks in it. Sometimes students will sub out holes, jumps, or breaks for other words that seem to be describing the same thing. A function is continuous if you can draw the graph of it without picking up your pencil from the paper or your marker from the whiteboard or whatever you're using to draw, right? If you can draw this thing in one take, that's what it means to be continuous. These aren't terrible definitions, but I'll tell you this, they're not great. I don't know what it means to go on forever in both directions. I mean, I kind of know what it means, but I don't really know formally what that means. I really don't know what it means to have no holes, jumps, or breaks. I don't understand what those classifications are perfectly, specifically breaks. I hear that word a lot. I don't really know. A function is continuous if you can draw the graph of it without picking up your pencil from the paper. My question is, do we have to draw the whole graph or not? Because if you're going to draw the whole graph of it, then you likely aren't going to pick your pencil up from the paper ever, because you're going to be drawing forever. So that's kind of a weird thing. But anyways, these definitions of continuity at best are pretty ambiguous. What I want us to do now is to take a look at these pictures of graphs and see if you can think about continuity in the context of all 6 of these graphs. All 6 of these things. Maybe I'll add some detail to the first one. What I'm drawing here is a vertical asymptote. I'm not going to hide that. I'm not trying to be coy about that. There's a vertical asymptote, whatever that point is. For the rest of them, think about continuity in terms of these functions. You can assume that there are little arrows on the ends here, unless, like right here, there's a point. So something like this goes on forever like that, and that, and that, and that, and that. All right, so go ahead, pause your video, write down, or at least think of, what continuity looks like in terms of all 6 of these functions. All right, hopefully you've thought about these 6 functions, and we've been able to piece together some bits about continuity for each. What I want to do is just give you a kind of summary for how students normally talk about these things. Now, this isn't going to necessarily match up perfectly with what you've thought, because students' opinions are varied here. What I normally do in a face-to-face class is we'll have students report back some ideas, and then maybe we just kind of take a straw poll like, hey, how many other people thought about this? How many other people thought about this? And so I can generally get a feel for what the dominant opinions are in a class. So let's go ahead and do that. The first thing is that this thing is not continuous. That's a pretty confident viewpoint for most of my classes. And it seems like this vertical asymptote is the thing that people focus on. This function, they say, yes, it is continuous. It's like our poster boy example of continuity, right? This one, people will normally say no, and they'll focus on this gap here in the domain of our function. Our function's not defined at this point, and so we say, hey, there's a hole. For this one, I get both yes and no. For the yes people, they say that, like, yeah, you can draw the thing in one take. It seems to go on forever here. For the no people, they focus on this ending point, and they say, well, there's something going on there, right? Maybe that has some problems with continuity. For something like this, maybe I will circle that point still. For something like this, people are pretty confident in saying, no, this is like classically not continuous, right? I should say over here, this is like a less confident no. And this one is sometimes a less confident no as well. They don't know how to kind of like figure out what's going on with this. Most students will say no, not continuous, but by now we might be thinking about, there's some tricks here. I've been kind of leading you to say like, hey, what we knew about continuity is wrong. And so people are likely thinking about like something on here might not act the way that we think. And so by the time we talk about these 2 examples on the right here, sometimes students will kind of get in their heads and they'll say like, maybe it's not continuous, but a couple people might say yes. Maybe you agree with that, maybe not, but this is normally what kind of student opinions are in my classes. What I want to do is just move on from there. We're going to just not address this until later. What we want to do is talk formally about some of the problems with continuity. So this is, again, something that I'll normally do with my classes. I'll say, okay, what was going on here? And instead of saying like, there's an asymptote, or there's a hole, or there's an ending point, what we want to do is try and talk about this in terms of calculus language. So we've been talking about limits in this whole unit in all these videos leading up to this. And so let's talk about limits maybe, and we'll see what's going on. And one of the first things that people will say is, wait a second, right here, we have an infinite limit. That means it doesn't exist. Cool. And again, we're only going to talk about the problems with continuity. So in this second graph here, a lot of students say that yes, it's continuous, so we won't really talk about it. For this one, our limit exists. Or at least it looks like it does, right? We have some graphical evidence that our limit exists. From the left and right side, it seems like we're approaching the same y value, whatever that is. So what's the problem? Well, it's the hole in the graph. That's what students will say. What is this? Well, it's a point in the an x value, that's not in the domain of our function. So our function doesn't exist. So that's our problem. Okay. We'll take a look at this one. And sometimes students will say, the limit doesn't exist. The right side limit does, but what's happening on the left? The limit doesn't exist here. Well, that's kind of interesting. We can talk about this a little bit later. Here, pretty classic example of a limit not existing. Left and right approach different things at all of these points. So we've got all these x values where limits don't exist. Notice the function values do, right? Even though there's these holes, our function is still defined at all these x values, not like this example over here. And then this one, notice the limit exists. Left and right seem fine. Notice the function value is defined here. So that means the function exists. This point is in the domain. What's the problem? Well, sometimes people will say, like, the point's not where it's supposed to be. Right? There's a jump here. Sometimes students will say that. Or sometimes students will say there's a gap. Or, I don't know, there's other words that people will talk about here. We call this a removable discontinuity because literally it looks like the point was plucked off of the line and put somewhere else. So what we'll say is that if this is some point with an x value of a, the limit as x approaches a of this function is not equal to the function value. That's our problem, is that whatever the y value is that our graph is approaching around a is not the same thing as the y value that our graph is giving out at the x value of a. That's our issue. All right, so all of that to say, for continuity at a point, here's how we'll define it. A function f is continuous at the x value a if the limit as x approaches a of f of x is equal to f of a. What we'll notice is that for this to be true, both the limit and the function value have to exist. So if we go back, you can see here on this example, our limit can't equal the function value because there is no function value. On this first example, our limit can't equal the function value because neither exist. The limit doesn't exist and our function's not defined there. Here, the limit doesn't exist even if the function values do. And so they can't be equal to each other. And on this one, they both exist, but they're not equal. So limits and function values have to both exist, and they have to be equal to each other at that point. Well, notice also this. This definition only talks about a function at one specific point. We do not classify this function as continuous. We say it's continuous at this point, at x equals a. So when we classify functions in terms of continuity, we're not classifying the whole function, we're classifying the one specific point. And then what we'll do is we'll say if these things aren't equal, whether because they both exist and aren't equal, or one of them doesn't exist, or whatever, then we say that this is a point of discontinuity for this function. For these 2 points over here, where the limit exists, we call it a removable discontinuity because it looks like the point was either removed completely or at least moved away from the line. If the limit exists, we think that this is we call this a removable discontinuity. But in general, we'll call these problems points of discontinuity. All right. What you'll also notice is that even if the two-sided limit doesn't exist, it might be the case that the left-sided limit is equal to the function value, or the right-sided limit is equal to the function value. Then what we can do is we can talk about one-sided continuity and say, all right, even if the limit doesn't exist because the left and the right don't match up or whatever, if the left side limit and the function value are equal, then we still have something. What we'll notice is that this kind of salvages this point right here. This, we can say, looks like it's continuous on the right, because this right-sided limit is matching up with the function value. You'll notice that also at all of these points of discontinuity, we still have one-sided continuity, right? Our function is continuous on the right at each of these points because the function value is matching up with the one-sided limit. With the vertical asymptote in the top left, we don't have one-sided continuity. There is no function value to match up with either a one-sided limit or the other. Over here, same thing, no function value. In this bottom right one, we do have a function value, but it doesn't match up with either the left or the right-sided limit. So we don't have one-sided continuity. So we can go back to this definition of continuity, and even if the two-sided limit doesn't equal the function value, if just the left-sided limit or just the right-sided limit does, we can still talk about continuity on one side. From there, if we're talking about continuity at a point, we can talk about continuity at a whole interval of points. Our definition, this is supposed to say R, not out. Our definition of continuity only talks about the function being continuous or not at a single point. Our previous idea was classifying functions, right, as a continuous function or a discontinuous function. And so it seems natural to move towards just talking about one point to talking about a whole interval of points. And so here's our continuity on an interval. A function f is continuous on some interval I. It doesn't matter if it's an open interval or closed interval, whatever, if the function is continuous at every point in the interval. If it is a closed interval, at least on one end, then we might not have the two-sided continuity there, but we'll say it's continuous on the interval if it's continuous on like that one side. So for instance, if I just give you this graph of the square root function, you might have recognized that function from earlier that we're looking at. And we had this point at the origin, and we said we were right-sided continuous here. We could say that this function is continuous on the closed at 0 up to infinity. So we can talk about continuity on the interval, even though it's one-sided continuous here. CONT'(s) is my short form for continuous because I get lazy when I'm writing things. So we can still talk about intervals of continuity on closed endpoints. What we'll do in the future is start figuring out how to find these intervals of continuity. I just told us what the interval of continuity was with this picture of a graph, and we can kind of connect this new definition to our old conceptions of limit and say like, yeah, okay, this interval seems to make sense because it doesn't look like there are any problems there. But we'll start doing that a bit more formally in the future. And what we'll also do is start investigating a bit more depth to continuity. Now, we won't have the full opportunity to talk about the full depth of continuity here. You can almost think that what we're doing is still a kind of misconception. It's still a bit of a limited model of continuity because there's some really interesting things that happen with continuity on domains of functions and different sets of numbers when we expand our thinking about limits a bit more and get a bit more formal. This normally would happen in like an analysis course or a topology course or something like that. And so it ends up being a bit tricky to talk about at a low level, like introductory calculus. And I'll put an asterisk on low because this is still college level math. But it takes a lot of work to build up the tools to talk about continuity at its full kind of beautiful, important part. So that's where we're at. We're going to talk more about continuity in the next video. We'll talk about finding these intervals of continuity and actually investigating what's going on analytically.